Welcome to Sci-Mind Machine. Today we're diving into one of the most mind-bending mysteries of the universe, time. What if everything you thought you knew about time was just scratching the surface? What if time isn't what it seems and reality itself bends around it? From wormholes and time travel to the quantum strangeness that makes scientists question if time can flow backward, this journey will push the boundaries of everything you know. So, buckle up as we set off into the heart of reality, where time isn't just ticking, it's twisting. Time is a fundamental aspect of the universe. It dictates our lives, from the moment we wake up to the time we sleep. We measure it with clocks and calendars. We experience it as a flow, a constant movement from the past, through the present, to the future. Yet despite its pervasiveness, time remains one of the most significant mysteries. What exactly is time? Scientists and philosophers have grappled with this question for centuries. Is it a fundamental property of the universe, as real as space itself? Or is it a construct of our minds, a way for us to organize our experiences? From the predictable cycles of day and night to the intricate workings of our biological clocks, time shapes our perception of reality. Join us on a journey through the fascinating world of time, from the everyday to the cosmic. We will explore the mind-bending theories of Einstein's relativity and delve into the strange realm of quantum mechanics. Prepare to have your notions of time challenged and your curiosity ignited. Our daily lives are governed by time. From the moment we wake up to the moment we go to sleep, time dictates our every action and decision. We wake up to the sound of an alarm, a jarring reminder that a new day has begun and responsibilities await. Rush to work or school, navigating through the hustle and bustle of the morning commute, each second precious as we strive to be punctual, and schedule our days around appointments and deadlines. Meetings, classes, and tasks fill our calendars, each with its own designated time slot. This innate sense of time is not merely a product of our busy modern lives. It is a fundamental aspect of our existence, shaping our behaviors and routines. It is deeply ingrained in our biology. Our brains are hardwired to keep track of time, ensuring that we function optimally in our environment. Deep within our brains, a tiny region called the suprachiasmatic nucleus acts as our internal pacemaker. This cluster of neurons is responsible for maintaining our circadian rhythms. This biological clock regulates our circadian rhythms, the natural cycles of sleep and wakefulness, hunger and alertness that repeat approximately every 24 hours. These rhythms ensure that we sleep at night and are awake during the day, that we feel hungry at regular intervals, and that our bodies are prepared for the demands of daily life. Our circadian rhythms are influenced by external cues like sunlight and temperature. The rising and setting of the sun, the changing seasons, and even the temperature all play a role in synchronizing our internal clocks. These external cues help to keep our biological clocks in sync with the environment, ensuring that we are in harmony with the world around us. However, even in the absence of these cues, our internal clocks continue to tick away. This remarkable ability allows us to maintain a sense of time even in complete darkness or isolation. This internal sense of time is not unique to humans. Many animals also possess internal clocks that govern their behavior, ensuring their survival and reproduction. Birds, for example, migrate with the changing seasons, traveling thousands of miles to find food and suitable breeding grounds. These migrations are timed perfectly with the availability of resources, demonstrating the precision of their internal clocks. Bees, too, have an impeccable sense of time. They know exactly when to visit flowers for nectar, ensuring that they gather food efficiently. And even tiny bacteria have internal clocks that regulate their cellular processes. These microscopic organisms follow daily cycles that are crucial for their growth and survival. The study of chronobiology, the science of biological timekeeping, reveals the intricate ways in which living organisms are connected to the rhythms of the Earth and the cosmos. It shows us that time is not just a human construct, but a universal phenomenon that binds all living things together. In the early 20th century, Albert Einstein shattered our understanding of the universe with a groundbreaking idea. Time and space are inseparable, woven together into a fabric we now call space-time. Imagine space as a flexible grid. According to Einstein, massive objects like planets and stars press down on this grid, bending it around them. And where the fabric bends, time slows down. This warping isn't just theoretical, it's measurable. Time actually runs slower closer to massive objects, which is why astronauts on the International Space Station orbiting above Earth's gravity age just a tiny bit faster than those of us on the ground. But here's where it gets even wilder. Near a black hole, where gravity is extreme, space-time becomes so twisted that time practically stops. If you were to fall into a black hole from the outside, it would look as though you were frozen in time at the event horizon, the point of no return. This phenomenon, known as gravitational time dilation, has mind-blowing implications. It suggests that the flow of time is relative. It stretches and bends depending on where you are in the universe and how fast you're moving. We're so used to thinking of time as a constant ticking forward. But in reality, it's as fluid as the stars themselves. And the strange part? This isn't just abstract theory. Every time we use GPS satellites, we account for gravitational time dilation to keep the system accurate. Without Einstein's insights, modern technology like GPS would drift by kilometers every day. Relativity is woven into the universe and even our daily lives, showing just how extraordinary and malleable time really is. Now we enter the realm where reality itself becomes almost surreal: quantum mechanics. At this level, particles like electrons and photons behave in ways that seem to defy common sense and even our understanding of time. Here, let's explore concepts like the Schrödinger equation and Feynman path integral, which force us to rethink how time functions at the smallest scales. IHPST equals sin h. In the early 20th century, Albert Einstein revolutionized our understanding of time with his groundbreaking theory of relativity. This theory fundamentally changed the way we perceive the universe and our place within it. Einstein proposed that time is not an absolute, unchanging entity, but is instead relative to the observer's frame of reference. This means that the passage of time can vary depending on the observer's state of motion and the gravitational field they are in. In other words, time can pass at different rates for observers who are moving relative to each other or who are experiencing different gravitational fields. This concept was revolutionary and challenged the long-held Newtonian view of absolute time. One of the most startling predictions of Einstein's theory is the phenomenon known as time dilation. Time dilation occurs when time itself slows down for objects that are moving at high speeds or are in strong gravitational fields. To illustrate this, imagine two synchronized clocks. One clock remains on Earth while the other is placed on a spaceship that travels at a significant fraction of the speed of light. As the spaceship accelerates, the clock on board begins to tick more slowly compared to the clock on Earth. This effect becomes more pronounced as the spaceship's speed increases. When the spaceship eventually returns to Earth, the clock on board will show that less time has passed for it compared to the clock that stayed on Earth. This is a direct consequence of time dilation. This phenomenon has been confirmed through various experiments, including those involving high-speed particles and precise atomic clocks. The implications of time dilation are profound, affecting everything from GPS satellite technology to our understanding of the universe. This is because time itself has slowed down for the spaceship in motion. The faster the spaceship travels, the more significant the time dilation effect becomes. This means that astronauts traveling at high speeds would age more slowly compared to people on Earth. Gravitational time dilation, another prediction of general relativity, occurs in strong gravitational fields. For instance, near a massive object like a black hole, the gravitational field is so intense that time passes much more slowly compared to regions with weaker gravitational fields. Time passes more slowly in stronger gravitational fields. This means that if you were to spend time near a black hole, you would experience time at a much slower rate compared to someone far away from such a massive object. This effect has been observed in experiments and is a key aspect of our understanding of the cosmos. Erwin Schrödinger's equation, a cornerstone of quantum mechanics that describes how the wave function, the mathematical representation of a particle's possible positions, evolves over time. This equation doesn't specify a direction for time, hinting that, at least in theory, time could move forward or backward. Richard Feynman took this even further with his path integral formulation, suggesting that particles don't just take one path from point A to point B. Instead, they take all possible paths, even those that seem to go backward in time. Feynman's revolutionary idea implies that particles can influence their past states, bending the rules of causality as we know them, IgM, m-piece equals sign 0. And then there's Paul Dirac, whose Dirac equation combines quantum mechanics and special relativity. His work predicted the existence of antimatter, particles that mirror regular matter but with opposite charges. Dirac's work led to the hypothesis that antimatter might move backward in time. This isn't just speculation. Antimatter annihilates upon contact with matter, releasing energy in a way that seems almost symmetrical in time. The mind-bending implications here are profound. If antimatter can move backward in time, it challenges the arrow of time concept from classical thermodynamics, suggesting that at the quantum level, time may be far less linear than we perceive. These groundbreaking ideas, from Schrödinger, Feynman, Dirac, and even John Wheeler, with his many worlds interpretation, have forced physicists to question if time is a one-way street. Wheeler's idea proposes that every quantum interaction branches into multiple universes, suggesting that in some of these realities, time might flow differently. So does time truly flow in one direction? At the quantum level, it's possible that time itself is just one of many dimensions, as complex and fluid as the particles that inhabit it. The math, Schrödinger's wave functions, Feynman's paths, Dirac's antimatter equations points toward a universe far stranger than we could have ever imagined. Section 4. Quantum time, a realm of uncertainty. While Einstein's theories revolutionized our understanding of time on a cosmic scale, the world of quantum mechanics presents even more bizarre and counterintuitive concepts of time. In the quantum realm, the subatomic world governed by the laws of probability and uncertainty, time itself becomes slippery and ill-defined. One of the most mind-boggling concepts in quantum mechanics is the idea that particles can exist in multiple states or locations simultaneously, a phenomenon known as quantum superposition. This has led some physicists to question whether time itself is not a continuous flow, but rather a series of discrete moments or ticks, like a cosmic clock. Even more bizarre is the possibility of particles traveling backward in time. In the quantum world, the arrow of time, the seemingly unidirectional flow from past to future, can become blurred. While we haven't observed macroscopic time travel, the strange behavior of particles at the quantum level continues to challenge our understanding of time's true nature. Does this mean every time we make a decision, a new timeline splits off? The implications are mind-boggling, hinting at a multiverse where infinite versions of ourselves could be exploring infinite possibilities. So time travel may be more than a journey through time. It could be a door to an entirely new reality. Section 5. Time travel, fact or fiction. The concept of time travel has captivated the human imagination for centuries. From ancient myths to modern-day science fiction, the idea of moving through time has always fascinated us. From H.G. Wells's The Time Machine to countless science fiction films and novels, the narrative of time travel has been explored in various forms. These stories often depict adventurous journeys to the past or future, sparking our curiosity and wonder. The idea of journeying through time holds an irresistible allure. It allows us to imagine a world where we can correct past mistakes, witness historical events firsthand, or glimpse the future. But is time travel merely the stuff of science fiction, or could it be a real possibility? This question has intrigued scientists and philosophers alike, leading to numerous theories and debates. Einstein's theories of relativity suggest that time travel might indeed be possible. According to his theory, time is not a constant and can be affected by speed and gravity. Though likely not in the way often depicted in science fiction, Einstein's equations open the door to the possibility of time dilation, where time slows down for objects moving at high speeds. One theoretical possibility is traveling at speeds close to the speed of light. As an object approaches the speed of light, time for that object slows down relative to an observer at rest. As we've seen, time slows down for objects approaching the speed of light. This phenomenon, known as time dilation, has been experimentally confirmed with particles in accelerators. If we could build a spaceship capable of such speeds, it's theoretically possible that we could travel into the future. Astronauts on such a journey would age more slowly than people on Earth. Imagine a journey where astronauts travel to a distant star and return to find that many years have passed on Earth, while they have aged only a few years. This is a form of time travel into the future. Another theoretical possibility involves wormholes, hypothetical tunnels that connect different points in space-time. These shortcuts could potentially allow for instantaneous travel between distant locations. If wormholes exist, they could potentially act as shortcuts through space-time. This concept, while speculative, is grounded in the equations of general relativity, allowing us to travel vast distances instantaneously or even journey through time. Wormholes present an exciting, albeit highly theoretical possibility for time travel. However, it's essential to note that both of these possibilities are highly speculative. The practical challenges of achieving such feats are immense, and our current technology is far from making them a reality. They rely on theoretical concepts and technologies far beyond our current capabilities. The energy requirements alone for such endeavors are staggering. Moreover, even if time travel were possible, it raises a host of paradoxes and philosophical dilemmas. Questions about causality, free will, and the nature of time itself come into play. The famous grandfather paradox, for example, questions what would happen if a time traveler were to prevent their own grandfather from meeting their grandmother, thus preventing the traveler's own birth. Such paradoxes challenge our understanding of time and causality. In conclusion, while time travel remains a tantalizing concept, it is firmly in the realm of theoretical physics and science fiction for now. The mysteries of time continue to inspire and challenge us, pushing the boundaries of our imagination and scientific inquiry. Whether fact or fiction, the quest to understand time travel is a journey that continues to captivate and intrigue us all. So, our perception of time isn't just a clock ticking in sync with reality, it's deeply personal, influenced by our biology and even our experiences. What if, by understanding and possibly manipulating these internal clocks, we could gain control over how we experience time? Could it be that our perception of time is as elastic and flexible as the quantum world itself? So, what have we learned? Time is a complex tapestry of different phenomena, from the way planets move to the quantum world's uncertainties. It shapes us, guides us, and even puzzles us. And while science has given us incredible insights, there's still so much to learn.